Hey guys, we're going to do probability. Now this is a big section, so let's dive in. So the first question on probability is question number 2. It says the probability of A and the probability of B are given and the events A and B are independent. So if we look at our study guide, it says that if A and B are independent, then to calculate the probability of A and B, we can just multiply them. So what does this mean to us? Well, this is what happens on our tree diagram. So each time we multiply this by this, if these are independent. So it's kind of like, let's say this was flipping a coin heads and tails, and this is maybe getting a heart, or I'll choose a spade, or not getting a spade. This is getting a spade or not getting a spade. Whether you get a spade in cards or whether you get a heads flipping a coin, in this instance, we flipped a coin and picked a card. Those are totally independent. So we would multiply in our tree diagram. And in that same way, if they're independent, to figure out if I got a spade, I got a head and I got a spade, you would multiply those, okay? So let's go ahead and do that. The probability of A and B, if they're independent, which it says they are, would be these multiplied. And so let's figure out what that is. All right, now that's not what they're looking for though, but we have a formula for that as well. So the formula says the probability of A or B is equal to the probability of A plus the probability of B, and then we have to subtract if there's any overlap, A and B happening. So if we think about this, this would be the probability of A happening and the probability of B happening, and we just calculated that both of them can happen at the same time. So we want to add the two together, but we want to subtract that overlap because we don't want to count it twice. All right, so the probability of A we get from our given, and the probability of B given, subtract the overlap. They do overlap. They are not mutually exclusive, and the probability of that overlap is a little more than 12%. So now if we combine them and subtract the overlap, we get 63, 52, and what do you know? 63, 52. All right, next question to do with probability is question 12. So let's dive in. It says a set of 10 cards consists of 5 red and 5 black. The cards are shuffled thoroughly and you choose one at random, observe its color, and then replace it. So this is important. That means our probability stays the same each time. The cards are thoroughly reshuffled. You again choose a card, you observe its color, then you replace it. This is done 4 times. So what are they doing? They're setting you up for a binomial. So in our notes, the bins is the elements to find out if it's binomial or geometric. So we notice here each trial is either a success or failure. We're counting how many red cards. So it's either red or not red. Right? It's independent, absolutely, because we have our replacement. And if I draw a card and I totally shuffle it again, it should be independent. Meaning I should have a 50-50 shot of getting a red or a black card each time. And just because I got a red card before and then I shuffle it, it should stay 50% the whole time. N, we know N because it says we're going to do this same iteration 4 times. And S, we know that we have the same probability each time, again, because we have this replacement. And that probability of success would be 0.05 because half the cards are red and half the cards are black. Okay, now I could put this in a calculator and figure out a lot of things, but I see N is 4, right? And P is 5, so we've found our answer, part D. No real calculations needed. Okay, question number 16 has to do with, oh yeah, this is a biggie. This has to do with probability as well. And now this is actually an example of a geometric distribution. And I am going to use my calculator for this. So it says two six-sided dice are rolled and the sum of their faces is shown and recorded. Let X be the sum required to obtain greater than 7. So that means I'm going to roll and roll and roll until I get a sum greater than 7. I know at this instance, I'm going to keep rolling until I get a 7. So that tells me this is a geometric distribution. Okay? So how could I possibly get a sum greater than 7? If I set up my sample space, right? I'm either going to do 1, 2, 3, 4, 5, or 6, or 1, 2, 3, 4, 5, or 6. I've got 2 die. Now if I get this, I got to roll again. If I get this, I'm going to still roll again because I got to keep rolling until I get a sum greater than 7. So if you think about this, these would be 7. This sum, 2 and 1, would be 3. That would be a 7. That would be greater than 7. And so if you see a pattern, we end up getting 7s. And if you ever played craps, which is a popular game in Vegas and over at the casino, 7 is the most likely outcome. Here are all the times you're going to get a number less than 7 and all the times you're going to get greater than 7. So we can figure out what's the probability of getting a sum greater than 7. We notice that there's 36 total, right? Because 6 times 6. And when we subtract 6 from 36, we get 30. So half of these would be greater than 7. The sums would be greater than 7, half wouldn't. So the probability of getting a sum greater than 7 on any single roll of 2 die would be 15 out of 36. Okay. So we meet the standard of geometric because that spells bits. It's binomial. Yes, I either get a sum greater than 7 or I don't. And if I don't, I keep rolling. It's binary, right? Because of that. I either get it or I don't get it. It's independent because we're just going to keep rolling. And no matter what I roll the first time, it shouldn't affect the second time if I really wiggle those dice around in my hand and shuffle them up, if you will. T reminds us of this. The trial is going to continue until, okay? And that's the setup. They didn't use the word until, but they laid the foundation for that. Notice we did this 100 times. And in this instance, they're saying I rolled 18 times. I only had to roll the dice once and I got one of these yellow outcomes, right? 23 times out of the 100, I rolled the die twice, and by that second try, I got a sum greater than 7, okay? So that's what this means, is that these are all the outcomes that I rolled my dice until. And S is to remind us we want to get the same probability each time. And we know that's true, right? That's our probability each time, okay? So now I can use my calculator and calculate this. And I can also eliminate answers. So I know that I can't get a sum greater than 7 if I never roll the die. So 0, that doesn't make sense. Like that doesn't make sense at all. Okay, so I'm going to eliminate that one right off the bat. And now using my calculator, I'm going to say menu. Stats, right? This is stat class. And I'm going to go down to the distribution. This is a distribution. And it's not on there. You have to scroll all the way down and find it, geometric PDF. And so you want to know what happens if, what's my probability of rolling a 1 the very first time, right? What's my probability of it taking 2 times until? Right? That's what that's asking me. So I'm going to go to geometric PDF. Clicking my buttons. And it says number of trials. So I'm just going to fit, what is the probability that I do it in my first trial? So when n is 1 And I know my probability of success is 15 out of 36. And in the calculator, you can just leave it just like that. So if n is 1 and, hold on, I accidentally did not hit geometric, so that's going to matter. Scroll, make sure you get geometric PDF. Okay, so probability of success, yeah, I take that back. Our calculator looks at it backwards. So probability of success is 15 out of 36. 15 divided by 36. And I'm going to put the value as 1. Okay, when I hit return, my calculator looks like this. It says geometric PDF 15 over 36, comma 1 equals 4.42. So this should be, if it's out of 100, it should be about 42 out of 100. So definitely E is eliminated. Definitely D is eliminated. Now it's kind of narrowed down to A and C. I'm listing toward A, right? We'll do one more. So let's say, what should be the likelihood of getting it taking me not on my first try, but maybe it took my second try. So I'm going to type this in again and just set 2 and see what that is. So using these exact same buttons again, statistics, distributions, scrolling all the way down for geometric PDF. I'm going to put in the probability of success again as 15 over 36, and my X value is 2 this time. Interesting, and I get 0.24. Now, I like this, but I like this even better. So you could keep going on this, but A is the answer, and I can see why. Nice work, guys. Now, number 22 also had to do with probabilities, so let's take a look. It says the distribution that represents the number of cars in a randomly selected residential driveway on any given night is this distribution. Remember, this has to equal 1, and these have to be a full set. So apparently it's not possible in this neighborhood to have more than 4 cars. Maybe it's an ordinance or something. So right now my cars are in the garage, so I'd be in this category. I guess 10% of people are either not home or maybe there's no cars in their driveway, right? So it says given that at least 1 car was parked in the driveway. So that means if we think of this as 100 people, that means 90 out of the 100 had at least 1 car. So what's the probability of exactly 4, given there was at least, so greater than or equal to 1. So I have to put that in the denominator. You can either put 90, that's me adding these up. I know that it's 90 because that's the supplement, right? Or the complement, excuse me. You could also put just the number 90. And then out of those 90 or 90%, how many had exactly 4? So we notice exactly 4 were 15%, or you can think of this as the raw number 15 out of the 100. So in both instances, either you take 0.15 divided by 0.9, or the raw number 15 divided by 90, we get 0.16 repeating. And so that rounds to 17, our final answer, 17%. Nice. Okay, question number 32 deals with probabilities, so let's scoot to that one. It says a standard deck of playing cards contains 52, 4 of which are aces and 13 are hearts. You're offered the following wager. Okay. So what if you had to draw 1 card randomly from the deck? You win $10 if you draw an ace. Okay, so the probability of success, the probability of an ace, is 4 out of 52. You can also look at this as the reduced fraction 1 over 13. You don't have to know that, but it's just, a common reduced fraction you use if you do a lot of gambling calculations, okay? So we have to, just like the last question, we have to build a table of outcomes in order to calculate an expected value. So when you look back at this table, we could have calculated the expected value how many did we expect to have in the driveway, which this times this, plus this times this, plus this times this, plus this times this, plus this times this. And because this number is big, I would expect it to be a number probably like 2 or 2.5. Yeah, it may be a little less than 2. It could be 1.9, something like that. You expect about 2 cars to be in the driveway in this neighborhood based on this data. In the same way, we have to build the table and then use that expected formula to calculate it. Okay, so let's do that. Either you're going to get an ace, okay? You're only drawing 1 card, right? 1 card. Or you're not going to get an ace. Okay, so what is the probability of an ace? It's this 1 out of 13. So what's the probability you don't get an ace? That'd be 12 out of 13. All right, so that's your probability. Now you have to put your winnings, right? So this is my winnings. And I also want net winnings, right? Because they want to know how much you would have at the end, because that's what you care about. So this is your probability of winning and your net winnings. So it looks like you lose $1 for playing. So yes, you're going to win $10, but you're going to lose $1 for winning. So your net winnings is $9. If your card is not an ace, then you just plain old lose $1. Okay? So that is your solution set there. And we can find the expected value of this game as taking 113 times 9 plus 1213 over 13 times -1. And so let's calculate what we get. Okay, I get -3 over 13. So using my simple calculator, so by 13. Okay, so you're expected in game 1, you're expected to lose on average 23 cents. I mean, the house has to win. That's how the casino keeps the lights on, right? It's not a game that you're likely to win if you played it over and over again. Now let's look at the other type of game. So this game says, again, you draw 1 card if the card is a heart. So either the card is a heart or it's not a heart. All right, and the likelihood of it being a heart, there's 13 hearts. So that would be the probability of a heart is 13 out of 52. Let me redraw that so it's clear. Which happens to be 1/4. There's only 4 colors, so 1/4. All right, so that means 3/4 of them are not hearts. That means they'd be diamonds, spades, clubs, and those are not the hearts, right? So what's at stake here? Either way you lose. So if it's not a heart, you're going to lose $1, okay? But it looks like this is more likely to happen, so you're not going to win as much. So here you win $2, but you lose $1 for playing. So your net earnings are just $1. So finding our expected value based on this game, we're going to take 0.25 times 1 times -1 times 0.75. And so it looks like we're expecting a fall out of 50 cents. So our expected lose 50 cents. Okay, so which one would you want? Would you rather lose 23 cents or 50 cents? Hopefully you would rather lose less money. Why? Because negative 0.23 is actually less than -0.50. Why isn't this one correct? It says because it has a greater probability of winning. If we look at the probability of winning, this is much less than that, right? You turn those into decimals, that's much less. So the reason, and they are not both equally favorable. So the reason is A. So our choice is A, wager 1, because it has a higher expected value. Both are negative, but just less negative. Last one, question number 40. The table provides data on political affiliation and opinion about death penalty of 850 randomly selected voters from the congressional district. Okay, so looking at our table, the way we test to find out if something is independent It's independent if the probability of A is equal to the probability of A given B. Or we could also say the probability of B is equal to the probability of B given A. So we have multiple things happening. It's like you're a Republican, you're a Democrat, you're an other, you're in favor or you're opposed. So they've set up a number of these to find out if these items are independent. And I want to jog your mind, what does it mean to be independent? So why does this mean what it means? So let me explain. We said in class, let's say we had 20 students, okay? But we didn't have very many boys. This happens, especially because the medical magnet program, it has more girls in it. So let's say 20% of our 20 students is, which is 4 students, have green eyes, right? But only 1 boy has green eyes. You might think, oh, okay, so knowing that you have green eyes, you're more likely to be a girl, because 4 out of the whole class. But then, if I told you that, so that means 4 hold on. I'm trying to set up the problem here. Where it is independent. So it's easy to see that, like, oh, okay, that would be independent. So let's see, 1 divided by 5. Let's say there were only 5 boys in the class. So 1 out of the 5 boys had green eyes. So what that means is that, and this is equal to 20%. 20% of all students had green eyes. 20% of the boys had green eyes. That means 20% of the girls. So that means there were 15 girls. Wait, that doesn't make sense. That's why I wanted to set this up before I turn the video on. So hold on. Yeah, screw my example. I think you kind of get the point. If the probability of green eyes is equal to the probability of green eyes given that you're a boy, right, is the same, then it's independent. Whether you have green eyes or not is not dependent on whether you have green eyes. Sorry, I couldn't set the numbers up exactly. Okay, so what do each of these mean? It's essentially saying each of these support the fact that it's not independent. Which one doesn't support that fact? Okay, so I kind of know which one it is just by laying it. I know that it's D, and the reason why is that this shows 2 out of this denominator, and that's not going to work because notice I have to compare to a conditional statement. And a conditional statement means it's not going to be over the full denominator. Notice here, each of these will be over the full denominator. Okay? So that's why you see these are over the full denominator. If I use the Lynch swap, I could reposition this and put one of these over the full denominator. Okay, so what is A saying? A is saying 299, this number, so that's the probability of Republican, given they're in favor of it. And they're saying that's not equal to 98, that's over 365, probability of Republican, given you're opposed. So these would be equal. It's kind of like saying green eyes given you're a female, green eyes given you're a male. If those are equal, that would show independence. Because they're not equal, that helps prove that they're not independent. So we will not pick A. Now let's take a look at B. B says that same setup, the probability of Republican given you favorite. And the next setup has this number over that number. So that's the probability of Republican in general. Notice if these were equal, we'd say they're independent, but they say they're not equal. So this would also help us prove they are not independent. Looking now at part C, 494. Okay, so that's the probability of favoring in general, because I'm over the total. And they're saying 299, that's Republican again, over that. Probability of favoring given you're a Republican. If they're equal, that's showing independence. They tell us they're not equal, so that would be another way to prove they are not independent. Jumping now to E, and let's piece this together. Could one of these numbers up here move down here and create a ratio? So the number 299 could be put in a ratio with either one of these numbers. So let's just pick one. We could say 299 over the denominator 397. So that would be equal to the ratio probability of favor given you're a Republican. And then what's left of my ratio is this 494 over 850. That's the probability of favoring in general. Notice they're telling us they're not equal, and this would have been a way to prove they were independent if in fact they were equal. That leaves us this. So what were they trying to prove? They're essentially saying this would be the probability of favor is not equal to the general probability of Republican. That would not, just because those are not equal does not mean they're independent, because you have to set it up based on a conditional statement, and that's what these formulas are for. Thanks for joining us, guys. Check out the next video for the next topic.